Network switching is the process of channeling data received from any number of input ports to another designated port that will transmit the data to its desired destination. The device through which the input data passes is called a switch. A switch network is made up of a collection of interconnected nodes known as switches. Switches are devices that may establish temporary connections between two or more devices that are attached to the switch. Some of these nodes are connected to the end devices in a switch network. Here is an example of a logical statement and its associated switching network. As you can see in the example, logic can even be used to simply electrical networks. You recall that equivalent statements in logic arrived at exactly the same results. That is, equivalent logic statements result in exactly the same truth table results. Using this concept to our advantage, we can find equivalent logic statements that are shorter and simpler. This translates into electrical circuits as fewer parts, shorter electrical paths, and quicker and cheaper electronic parts. Let's do an example. Here is a given circuit that we are to simplify. Our first step, to translate the above switching network into a logic statement, which we then will analyze by doing a truth table. Here, you can see that I made a truth table with the final result of the truth table above the arrow. This statement comes out to a tautology. What's a simpler statement that is a tautology? There are many, but P or not P came to mind first. Since they are both tautologies, they must be equivalent. Now that we know that this is equivalent, our new simplified circuit would be diagrammed like this.
As shown in Figure 5, series and parallel circuits can be combined to form more complicated networks. The network there corresponds to the statement P and Q, not OR. If we think of the switches as drawbridges, we can see that we are able to go from A to B when both P and Q are down or closed, or when R is down or closed. Now, all compound statements can be represented by switching networks. When switches open and close simultaneously, the switches will be represented by the same letter and will be called equivalent. Switching networks, a problem-solving tool. I have here the table number 1 example. So notice that in the networks of Figure 5 and 6, current will flow if P and Q are closed or if R is closed. For this reason, these two networks are said to be equivalent. In general, two networks are equivalent if their corresponding statements are equivalent. For example, the statement corresponding to the network in Figure 5 is P and Q or R, and the Figure 6 is P or R and Q or R. The truth tables of the because two statements are identical, so the networks of figure 5 and 6 are equivalent. Finally, we shall consider the design of certain networks having specified properties. An equivalent problem is that of constructing a compound statement having a specified truth table. The procedure used will involve the basic conjunctions given in Table 1. For example, a network associated with a statement having truth table TTFF will be the one corresponding to the statement. Here in this simple example, the lamp or L is connected to the battery supply. Vs via the normally open switch S1. Thus, if switch S1 is not pressed and therefore open, no current flows so the lamp will be off and not illuminated. Likewise, if switch number 1 is pressed, closing it, then current flows around the circuit and the lamp will be on and illuminated. Under normally steady state conditions, the switch is permanently open, so the lamp is off. We can use switching algebra to describe the operation of the circuit containing the switch is 1. For example, if we label the normally open switch as a variable with the letter A, then when the switch is open, that is A is not pressed, we can define the value of A as being 0. Again, when the switch is closed, that is A is pressed, we can define the value of A as being 1. This switching algebra theory is true for all normally open switch configurations. Switching through table. We can develop this switching theory idea further by saying when the lamp is on or illuminated, each switching algebra variable will be 1, and when the lamp is off or not illuminated, each switching algebra variable will be 0. Thus, when the switch is pressed or activated, the lamp is on, so A equals 1 and L equals 1. And when the switch is not pressed or unactivated, the lamp is off, so A equals 0 and L equals 0. Therefore, we can correctly say that for the switching theory of the lamp, L equals A as shown in the truth table. The type of switch used in the above example is called a normally open make contact switch, as the have to physically make it for the switch to be considered closed, or A equals 1. But there is another type of switch arrangement, which is the exact opposite in operation of the switch above all, a normally closed break contact switch, which is constantly closed.